Mais j'ai pas le poster.
Planck Herschel synergy.
Yeah. Ambitious. Are we ready?
Okay, so if we could make a start. Continuing on the theme of complementarity of Planck with other experiments, our next talk, the Planck-Herschel synergy, will be given by Montier from the IRAP and the Planck collaboration.
Good morning, everybody. I first want to thank the organizers for giving me the opportunity to give you this ambitious program, Planck-Herschel synergy. And I will try to give you a panorama of what has been done and what has to be done between these two huge missions. So, as you know, it's a long story between Planck and Herschel, and it started in 1996 when the two satellites were merged in the same Planck-Herschel mission. And, well, I have to say that they fit quite well in the same launcher. And so they travel to the L2 point and they provide such nice results from both sides. Here is a brief overview of the two of the instruments on board on Planck and Herschel, and that you already know Planck, so I will not give you that again, but just a quick comparison with the Herschel instruments. You have packed, spire, and hi-fi instruments. And so two are imager and spectroscopy, and the high-resolution spectroscopy capability. And here the resolution, of course, of Herschel is much better than the one of Planck by a factor of almost 10. And the sky coverage of Herschel and Planck are complementary. So while Herschel goes to cover the bump of the dust emission, galactic dust emission, Planck goes much out to the millimeter, but we have here two bands that overlapping between Planck and Herschel that will be very useful. And of course, Planck is a full sky observer when Herschel in observatory. So as a result, with Planck we have the full sky, and with Herschel we have this nice picture of the compilation of spire, packs plus hi-fi pointings that cover the whole sky, but only a small fraction of the sky, so 5 to 10% of the sky. So of course here we have a nice complementarity between this full sky of Planck and the low coverage of Herschel. So this is the outlines of my talk, and we just illustrate what synergy means, because I will show you how Planck can help Herschel, how Herschel and Planck link the similar scientific results from small to large scales, and finally how Herschel can help Planck on especially using the high resolution capability of Herschel and for the point sources. So first thing, the Planck-Herschel intercalibration. As you know, with Herschel you have high resolution, but you miss the large scales. So here is a nice batch of high-gal program here in the inner galactic plane, only 2 degrees width, and you don't have the offset, the absolute map level of this map. But with Planck, we have the whole sky, so we have a way to calibrate the absolute level of the map using correlation with H1 to get the galactic absolute level, or correlation with the CIB model to get the CIB monopole absolute level. So we can combine Planck and Herschel to give the offsets to Herschel maps. So the idea is very simple. You can use the two Planck bands here, IRAS bands here, and you use a model of SCD, and you build a model for the Herschel bands. And then you compare the model based on those data with the smooth data from Herschel. You make the correlation, and this gives you the offset and the gain. But the gain was not distributed during the mission, only the offsets. And this is an illustration of such work done on the Herschel high-gal program. So I remind you that high-gal was performed to map the full galactic plane, a two degree band, and each of the 2 by 2 degree fields have been calibrated using this method. So the offset have been put on each field. And you see that we have a very good agreement after mosaicing here. And we have no signs for brightness mismatch anymore. So finally, since 2009, so at the beginning of the SDP field, Herschel SDP fields, Planck offsets have been determined for many imaging Herschel programs. The High-Gal, Gould-Belt, Heritage, Hobbies, and Galactic Call Cores. And finally, it's about 30 Herschel papers use these offsets for their analysis. Now, these kind of offsets are distributed by the Planck Legacy Archive. And I remind you there is a poster by Bernard Schulz on that here in the hall. Okay, after that, after the offset intercalibration, we have the gain intercalibration. And we have to say that with Planck, calibration philosophy was first to make the correlation with FIRAS data. But after a few tests, this has been changed to planet calibrators, as Herschel does. And the a posteriori check here is very good. You have the correlation between Planck and Herschel at 545 gigahertz. And you can see that the agreement is very excellent. For the other band here, the 857 gigahertz, the agreement are within the uncertainties that are 10% and 7% for Herschel. But the agreement is very good. Okay, now I'd like to illustrate nice results that have been found for Planck and Herschel concerning the large scale. And on first one, on the galactic science. So in 2011, the Planck has shown that there is large variations of the submillimeter emissivity between the Milky Way and local galaxies like the Large Magellan Cloud and the Small Magellan Cloud. So here are the values that have been derived from Planck data. So from 1.2 to 1.8. And the same variations have been observed at high resolution with Herschel here. This is a list of papers that have measured this, what is called the 500 micron excess here, that you can see here, that the beginning of the flattening here of the opacity. So both missions have observed the same behavior of the dust emissivity, and the origin is still unclear now. It could be in principle due to existence of extremely cold dust, or a modification of the optical dust properties. Another nice result is this one. The galactic gradient of this 500 micrometer excess has been observed in High-Gal first here. So this is the 500 micron excess that is lower in the inner galaxy and higher here in 60 and minus 60 degrees outside the galaxy. So when the excess is lower, the flattening, the spectrum is flattening, so the spectral index is higher. And when you look at the Planck map, all-sky Planck map, we are zooming in this small region here. You see exactly an increase of the spectral index in Planck. And if you zoom, you have a very nice match between the blue structures here and the red one here. And it's quite impressive. So Planck and Herschel are totally consistent on this kind of analysis. The power of Planck here is to increase the analysis over the whole sky, and you can see very nice gradient from the center to the outer galaxy here with Planck. And nice comparison also about the Andromeda galaxy here. You can see the Herschel result with the same kind of gradients, with a spectral index higher in the inner galaxy compared to the outer galaxy. And the same observed with Planck, again, even if these results are still preliminary, and Michael Peels have already presented that yesterday. So again, Planck and Herschel find the same kind of an analysis, and it's very consistent. Now, of course, another large-scale analysis is the CIB analysis. And here is a comparison of the power spectrum of the CIB in the two common bands here, between Planck. So we have two estimates of the power spectrum of CIB with Planck, two versions, the black and red, and the Herschel estimate here in blue. And first, while the Planck, two Planck versions are not completely consistent due to calibration improvement between the 2011 and 2013 version, you can see that between Herschel and Planck here, you have a very good agreement between the two power spectra. And in that band, 545 gigahertz, the power spectrum are within the uncertainties. Even if you can see that you have quite difference here, but I will tend to more believe the Planck result here because we have the large scale with Planck, so we have the low L here, while Herschel does not have that. Okay, I will now focus on another very interesting capability of Herschel, the high resolution data, and how we can use Herschel as a microscope pointing at the Planck blob. So first observation, very simple. Here is the Planck beams in the high frequency bands of the instrument, so 4 to 5 arc-minute, compared to the Herschel beams here. So it's quite impressive. Of course, Herschel, it's better designed to look at point sources, of course. And with Planck, we have a full sky, so the PCCS, the Planck catalog of compact sources that Joaquin presented yesterday. And we have many sources, but many sources, 5 arc-minute sources. While with this key program Herschel surveys, galactic and extragalactic ones, you have thousands of galaxies at a very much higher resolution. So how first Herschel could help Planck in that field? So the idea is that with high resolution, you can unveil the nature of the Planck blobs and what can Planck could provide more. And because we have lots of statistics over the full sky, we can probe the variety of the galactic environments here for the galactic sources, or we can also explore the rarest but bright enough sources, extragalactic objects. And I will detail these two projects here, the first on the cold clumps, and here on the high Z Planck candidates. Sorry, like that. Okay, first, I just want to illustrate how Herschel has been used to calibrate the PCCS at the high frequency channels. First, to estimate the level of spurious here. So this is the Planck map on the Polaris, and you look here at the same Herschel map at the same region. So while Planck is picking few sources that seems to be sources with Planck, when looking at Herschel, there are only cirrus contaminations. So thanks to this comparison, the choice of the signal-to-noise ratio has been set to reject contamination by cirrus using Herschel. Another thing has been done for the completeness here, and by comparing the flux of Planck sources as a function versus the Herschel flux, you can see here that the saturation of the flux that gives you the completeness flux limit. And that has been used to build the PCCS. Okay, now I'd like to present you one of the interesting synergy between Planck and Herschel, the Herschel follow-up of Planck galactic cold clumps. Just to remind you the context of this study for the one who are more CMB and not galactic guys. This is the naive picture of the galaxy. You have the galactic plane here with this scale, 30 kiloparsec size. Inside here you have the star-forming clouds that are 10 to 100 parsec width, and you have here small clumps or cores that are much smaller, 0.1 to 1 parsec. And the aim of Planck was to have statistic of these small sources, small clump, over the whole sky. So thanks to the Planck design, we have high frequency bands here that are suited to follow the cold emission of the dust. So here is the comparison of 4 SEDs at various temperature that are on the top of a cirrus SED, typical cirrus SED. And you can see that here Planck is clearly designed to pick up these sources with very low temperature. So we use this capability, and we combine IRAS and Planck data with the so-called Coco-Codet algorithm to build an all-sky catalog of cold sources at a 5 arc-minute resolution. And the first version of this catalog has been already released in the earlier released compact source catalog, as called the ECC, the Early Cold Core catalog, with 915 objects, very low temperature, below 14K, and high SNR. And so this is already public. And the full version of the catalog will be released soon with about 9,000 objects in this catalog all over the sky. So, yeah, we have lots of sources in the galaxy at a 5 arcminute resolution. But what are they? Are they really cold clumps? Are they serious filaments? So to unveil that, there is a Herschel key program called CORES, Pierre Mika Juvela, and we have followed up 120 fields all over the galaxy here. So you have the white dots are the points where we have followed up. And we have 350 Planck cold clumps that have been followed up. And these have been just completed. So we can study the early phases of star formation at the galactic scale and the impact of the environment. This program is complementary to other Herschel programs, that Goulbels, Huygens, and EPOS, that are concentrated of star-forming regions. And here we have high-latitude objects, for a few, and we are looking outer of regions of known star-forming complexes. We also have large distances here inside the plane, for a few, and we have selected cold regions already. Okay, so now, thanks to Herschel, we can go from the Planck cold clumps to the Herschel cold cores. And this becomes really interesting here. You see, I don't know if you see the Planck contours on the maps here that are matching very well the substructures of Herschel. And you see rich and complex substructures within the Planck clumps, of course, but all are mostly colder and denser than the whole blob. And they also contain embedded warm sources, young stellar objects, YSOs. The morphology of these clumps is quite various. We have isolated objects, cometary globals, and filamentary structures, but only half of the field are filamentary, while lots of other Herschel observations based on of star-forming region stated that everything is almost filamentary. Only half of this field are filamentary. So we have other interesting environments, like a few of them, like this one, the Polaris, indicates the dynamic interaction with the environment here, like triggering or things like that. And the filaments have typically width of a few 0.1 parsec, compatible with Herschel observations, and most are gravitationally unstable. And we can even look further inside these clumps. So now we have, this is called Planck clump here. Well, with Herschel, you can see the structures, and with WISE, Akari, and PAX data, you can show that many cold clumps are already association with star formation. So you have the star evolution here in blue. The small cores are starless, and they have class 1, class 0, 1, and 2 in colors here. And you can see that even in cold clumps, you have lots of starless and even already evolved stars. And on this map, it's really interesting. You have the temperature. So these clumps are cold, very cold. And you can see in WISE that they are bright. So it means that even cold, they coexist with young stellar objects at the same locations. Finally, we observe that the ratio of the young stellar object versus starless cores is about 30% in these fields. So, few results about this Herschel key program on cold cores. We have derived the dust properties of these objects, and we observed an anti-correlation between the spectral index and the temperature that is steeper than expected effect of observational noise. And with that, temperature variations tend to create a positive correlation. So these observations are mainly due to optical properties of the dust. Furthermore, on few fields, we observe an increase of the dust opacity from diffuse to dense medium. This has to be extended to the complete set of fields. But finally, intrinsic depth properties evolution must be understood and taken into account if you want to better estimate the key parameters at the mass or the density of these cores, and these properties has to be described properly. So we have a lot of statistics, 350 objects. So the work is ongoing on that, and we have still lots of things to learn from this follow-up. Okay, now I would like to show you another Herschel follow-up, but not on galactic sources, but high-Z extragalactic candidates. So just to remind you the context of this, here you have the nice view of the CIB at the pole, and the extragalactic view is composed by nearby galaxies here, very close one. We have the galaxy clusters that are detected with the SD signature, and you also have cold overdensities here, the red dots in this structure. That may be large structures alignments, or simply lensed sources, or protoclusters. I mean, very native clusters or groups of galaxies. And we are looking for these objects, and the predictions say that we may find 100 to 1,000 such objects in the full Planck sky. So the idea was to look at those ones, and we perform a dedicated method to search for these sources in the Planck maps. Again, we use the full capability of Planck here using the high frequency bands, and we can separate the bump of the SED of redshifted sources here that are between the CMB and the cirrus contamination. So using all these bands, we can separate that. So we clean from CMB, galactic cirrus emission, and we look at the excess here after cleaning, and these give you sources that are bumping in that area, so high redshifted sources. I want to stress that it's not an SZ detection. We are not looking at positive SZ signal. We are looking at the submillimeter dust submillimeter signal from the star-forming, actively star-forming galaxies inside these groups. And finally, we have an original list of hundreds of Planck high-Z point source candidates, over 30% of the sky. But again, we see overdensities of the CIB. What could it be? So we need Herschel follow-up at high resolution to unveil the nature of these objects. The first way to do that is to cross-correlate these candidates with available Herschel surveys. So that has been already discussed by Clements and Desotic here. They look in the H Atlas and Hermes fields, and only a few candidates are falling in those fields because they are even big. They are quite small compared to the full sky, of course. And we have a few interesting confirmations ever. We have lensed dusty galaxy here at redshift of 3.26, and another lensed galaxy at redshift of 5.2. And those are also available and visible in the Planck data and detected with this algorithm. Another way to do is to perform a dedicated follow-up of these candidates. So we have here a set of 3 follow-ups that have been performed, and with a total of about 230 candidates, Planck candidates, that have been followed up with Herschel. This is the location of these candidates on the cleanest regions of the sky. So a few examples of the first results that we get from that. We have first confirmation of, we have a Herschel confirmation, of the first Planck lensed galaxy here. This is the Spire map of this. This is really bright, so it's 400 millijansky at the 350 micron. This is the SED of the Spire SED here. And so you can see that it's really high redshifted. And we have other follow-up, because Herschel is not enough to really unveil the nature of that. So we have CO spectroscopy follow-up with a redshift, confirmed redshift of 2.6, and nice imaging with the PDB interferometer here, when you see the lensed images here of interacting galaxies. So this object seems to be highly magnified, above 10, but we are waiting for lensing modeling and to go further. Another kind of object is the first confirmation of a Planck protocluster candidate here. So these are the Planck data, where you can see the excess at the center in the Planck bands. This is when you can zoom with the Herschel spire bands, where you can see very nice excess in the 500 micron here, revealing the hazy nature of this object. And when you look with optical data, CFHT, and near-infrared data with Spitzer, you can see an overdensity of J-K galaxies here. And the overdensity is speaking in this region of the Herschel blob, so this region here. And we also have spectroscopic redshifts using VLT, revealing two groups of galaxies. One group is 1.7 and another group is at redshift 2. So instead of finding a protogroup of cluster, we find two protogroups that are too far to be linked together, but we find two groups. I'm done. Okay, this is a nice Herschel follow-up gallery just to illustrate the morphology of the objects we have in this follow-up. Few are very compact, like those one. We have few Herschel Spire 500 micron sources here. You have a few that are lens, like those one, completely isolated, and more extended sources. So on this follow-up Herschel of Planck hazy candidates, just a few words. First, Planck is unique because we have an all-sky blind multi-wavelength detection algorithm that provides a list of hundreds of hazy candidates at a redshift greater than 1.5. But Planck alone is nothing. I mean, we need something else. So Herschel here is crucial. And a few candidates have already been confirmed, a protocluster and a lensed galaxy, but we have other 8 lensed candidates that have to be followed up and that are very bright, so hundreds of millijansky. So the first elements of statistic on this sample is that we have 85% of our sources are red over densities in Herschel, and a very small fraction, 5%, are lensed galaxies. So Planck appears to detect the rarest but bright enough hazy environment in the submillimeter all sky, and is very powerful. Well, now, is it the end of the story between Planck and Herschel? As you know, satellites are both down or almost down. It's a matter of day for Herschel. And so I would say no, we can look at combining the data. And we have many things to do, and we have lots of data. So we can link the small and large scales here. And concerning the Herschel follow-up of Planck sources, we have lots of things to do because lots of statistics, lots of things to understand. And something interesting also would be to exchange the tools between the Planck and Herschel community to apply the same algorithms and same thing. And this has been done already, but not fully, like the detection of filaments in Herschel has been developed a lot, that is to be applied in Planck. And also the detection of cold sources in Planck can be applied to Herschel data to find cold overdensities in high resolution. And finally, we still have in more than 1 year Planck polarization data. And I think it will be very useful to combine the Planck polarized data with the high resolution Herschel. Okay, thank you very much.
Okay, thank our speaker. Just, I think we have time for maybe 1 or 2 quick questions. Okay then, so let's thank our speaker again and then we move on to the next talk.